Should we get started? Yeah?
Yes. So we have Pierre.
Yeah. Part 4. Hi, everyone. So actually, I'm going to go back to the third deck of slides. I was not intending to cover everything, but in order to understand some of the numerical results I'll show today later, I just want to sort of restart a little bit from last year's slides. And in particular, there was this idea that perhaps we could couple chains in such a way that they meet exactly at some point, if you remember. So those chains are your MCMC chains. Again, maybe here we have to think that we have already designed the MCMC or it's been given to us, and we're just trying to, we could just run the MCMC for 10,000 steps, report the output, the ergodic average, but maybe there's something convenient in not just doing that, but in particular in using couplings. So here we are imagining pairs of chains. The second chain Y has the same marginal distribution at time t than x. So neither of those chains is stationary. They both start from pi 0. But are constructed in a very specific way so that they meet with this lag. Okay, so there's a time tau at which the two chains coincide, but with this lag. So the main topic for today is to explain to you in some simple examples how we can obtain those chains that meet exactly. It's not obvious. Some of you have noticed, have been wondering how we're going to obtain the chains that meet exactly, especially on a continuous state space. So even if you have a simple AR1 process with Gaussian noise, if you sample two AR1 processes independently, they will never be exactly at the same location. And so, of course, we're not going to sample them independently. We're going to couple them in a specific way. I want to start maybe the first bit of this lecture by listing a few advantages of being able to do that first. And then I'll promise at least we'll cover the AR1 case and a few more cases. Okay, so why would it be interesting to implement such couplings? So we talked yesterday about unbiased estimators. So with this telescopic sum trick, it turns out that if we can generate those coupled chains, we can obtain an unbiased measure, an unbiased sign measure that approximates pi in the sense that if we generate many of them in parallel and average over the independent parallel copies, we would get consistent approximations of pi because we would be averaging variables that have the correct expectation. So we'd have a very standard law of large number and even central limit theorem if the second moment is finite. And so that's a pathway towards parallelizing MCMC calculations. Okay, so there was a connection with the Poisson equation. So it turns out we don't do exactly this procedure. We do something more complicated. So here I'm going to leave those interested among you to look at the slides or the papers to have the details. But the idea is that, of course, unbiasedness is not the end goal. We'd like an efficient procedure. So we're interested in the cost. We're interested in the variance. And so there are results now about that. So in particular, so we have results conditions under which the proposed sign measure, so this unbiased estimate, has a finite p moments. Not just finite one moment, but p moments. And then we're interested in what's called the asymptotic inefficiency. So that's the expected cost of an estimate times its variance. Okay? And so this is the quantity you want to minimize when you have unbiased estimators, in the sense that if you have a more expensive one, then you can produce fewer of them in a given time budget. So if it's more expensive, but it reduces the variance, it could be worth it. And it turns out in terms of, if you parameterize your CLT by budget in terms of number of copies, this is the right quantity that you like to optimize. And so this variant of this coupling estimator that flashed very quickly here, it looks a bit complicated. There are like different tuning parameters, which are integers. The idea is that by tuning them correctly, you can achieve asymptotically the same efficiency as the original MCMC algorithm. So you're not doing better in efficiency. You may be doing more or less the same, but you have the benefit of being able to then parallelize. So that's the. Well, I'm going to be very quick on this, but it is well. I hope it's well documented now in the literature. So we have results sort of justifying that basically, as you tune the parameters in a certain way, your asymptotic variance would be the same as in the original MCMC estimate. So you can, which asymptotically was unbiased. The original MCMC estimate, if you do a lot of iterations, the bias disappears. So in a sense, it's the least that you can require that the cost of removing that bias would not be too large. But it turns out, thankfully, that it's the case. So you can do plots like this, for example, where you have the inefficiency relative to MCMC. So here the hope is to get to 1. So that's the inefficiency of the method, cost times variance, divided by the inefficiency of MCMC, which is basically the asymptotic variance times 1 because we count the cost of one iteration as 1. So the goal is to get close to the MCMC efficiency, but having this non-asymptotic unbiased property that allows you to do parallel copies. So here we see that those tuning parameters, the lag, for example, if we tune it well, we get close to this horizontal line. That's the good efficiency line. But on the other hand, if you don't do it well, you could be 10,000 times less efficient. So just to say that indeed you don't care only about unbiasedness. If you were to use the most naive versions of those estimators, basically the variance would be massive. Okay, so just one thing that I'm going to present that is not just unbiased estimation, but maybe more concretely trying to answer the questions that I laid out initially about how many steps should we do with MCMC. So it turns out those lag coupled chains can provide an empirical answer to that. And there are like related results in the literature for a long time, like Val Johnson's paper in the 1990s, but I'm going to present just the proposed diagnostic. So it is nearly the same reasoning as before. You're interested in the distance to stationarity at step t. So the total variation distance between the marginal distribution of the chain at time t and the limiting distribution, the target distribution. And t is fixed here. T is not going to infinity. So like before, we do a sort of telescopic sum argument. So here the TV satisfies the triangular inequality. And so this is always less than if we compute TV distances at a lag of L. So we have PT plus L minus PT plus 2L minus PT plus L, and so on. We're going towards infinity in steps of length L. Okay, so here we are. Obviously, this is a loose bound. We're using the triangle inequality. Next, one of the representations of the TV is in terms of an infimum over couplings. That was one of the representations. So if you take any particular coupling, you get an upper bound on the TV in the form of a probability that a variable that would follow the first distribution would be unequal to the variable following the second. Okay, so we have an infinite sum of those probabilities of things being different. Of course, in general, if your coupling is, for example, independent, then this is equal to infinity. So the bound holds and is not very useful. In fact, the TV is always less than 1. So the only useful upper bounds are the quantities that are less than 1. If your upper bound is equal to 2, you haven't learned anything. So here we don't know yet what those upper bounds are going to be. And here I'm doing, as before, a swap of expectation and limit. Again, not always legal, sometimes legal. Oh no, I'm not doing it yet. I'm going to do it later, sorry. So here I'm just writing that the event that those chains are different is the same event as saying that the meeting time occurs later on, if it occurs. It hasn't occurred yet, because from the meeting times, the chains are equal. And then I'm going to do the swap of expectation and limit. And I'm simplifying the expression. So if I'm just swapping expectation and limit, I have the expectation of the number of indices j such that tau is more than t plus jl. You can count how many integers there are there. and it's equal to that number, the ceiling of tau minus L minus T divided by L. Okay, and so you end up with this upper bound on the TV in terms of an expectation of this function of the meeting time, simple function of the meeting time. Okay, and that's the meeting time between two chains, and neither of which starts at stationarity. So that's the big difference compared to the coupling arguments in the theoretical literature, where one of the two chains starts at stationarity. So now you have an expectation that you can, in fact, estimate. You're drawing chains until they meet, run them until they meet, do that many, many times. It gives you an empirical distribution for the meeting times, so you can then estimate an expectation with an empirical average. It could be non-informative in the sense that if it's larger than 1, you don't learn anything. But note that mechanically, this will decrease with t. At some point, if tau is going to be it's a random variable, but it's going to have a certain distribution. So if you take very large t, eventually it's in the right tail of the meeting time. And so this quantity will go to 0. Okay. So there's a hope that at least for certain t large enough, this is actually going to be a practical quantity. Yeah.
So you mentioned yesterday and also in the paper that L, the larger L the better is the bound.
Yes, to some extent.
I wonder, is there any lower limit on L that is needed?
Yeah, so in principle, it's true that if you increase L, you're going to get a better bound up to a certain point. You can see it in a sense because when you take bigger steps towards infinity, you apply the triangular inequality fewer times, so you're losing less at this stage. On the other hand, the procedure first starts by doing L steps of the first chain before you try to propagate them together. So your cost is linear in L. So in practice, you can't take L to infinity because you have to do L steps of the first chain until you start the second chain and then run them until they meet.
Tau was defined before the third line. What is it?
So tau is the meeting time, so
Okay, so
it's a crucial quantity. It's the first time at which xt equals yt minus L. In fact, in my construction before, it could never happen before L plus 1, I think. Because, you run the first chain on its own, and then it's at time L already, and then you start coupling with the second chain. So meeting is not going to happen before, unless by chance, but on continuous state space, it will not have happened before. So x0, yeah, thanks. It's useful probably to remind this. Here's the procedure. And then you do xt given xt minus 1 running on its own, basically, using your Markov kernel for t steps. And then you couple. So you generate xt, yt together from the coupled kernel, given the previous states. Sorry, it's yt minus L, because I'm propagating them with a lag. So I generate at a certain point xt and yt minus L. And then, there's a whole game of what's the best coupling. The best coupling is going to be the coupling that leads to the shortest meeting times. And here you see that it will give you a lower bound. So here in this expression, you really see that the meeting time tells you a lot about what's happening, even marginally on the chain. And what's nice about this, so I haven't mentioned at all the existing convergence diagnostics for MCMC, of which there are many. There are survey articles on convergence diagnostics or output analysis for MCMC. And many of them rely on some sort of asymptotic argument because asymptotically we know what should happen, so we can test whether we're there or not. But under the null hypothesis that we're there, so there's always this kind of cyclicity in the arguments, whereas here t is really fixed. It could be t equals 0. Okay, so yeah, that's the idea. There's no assumption on pi 0 whatsoever. Right? So you could be starting very far away from stationarity. And then you, practically, what you're doing is you're approximating this expectation by an empirical average over R independent copies. You have to choose L also, right? So typically by default, I would choose L equal 1, and then I see what the shape of the meeting times look like, and then I revise my choice of L. But it's very empirical at this point. And you can upper bound other distances than TV. It's very direct with any distances that have a coupling representation, because a similar argument as here works. So if you have the Wasserstein distance, it's an infimum over all couplings of an expected distance. So here, instead of having this probability, you have an expected distance. And so what you're then computing is the distance between the chains up to the meeting times, after which the distance is 0. So here's the type of plot that you can get. So from here, in a toy example, but I'll show you more of those today. So you generate all of your meeting times, maybe 1,000, for different lags. So here I show you the bounds for different lags. And I'm computing, using an empirical average, the previous bounds for different t's, different iterations. And so here it's in TV, so you see the TV is always between 0 and 1. So at all those times, I'm not learning anything. So with, for example, the choice of lag equal 5 here, I'm not learning anything up to time 200, more or less. And then I'm learning something, in the sense that my bound now is not vacuous, and it's going to 0. So this is a log scale, so here you have a nice geometric convergence. And if you increase the lag, it costs you more, because you have to start the first chain with L steps. But your bound gets lower up to a certain point. At some point, it's never going to be sharp. It's never going to be sharp, because the coupling that you're using is not necessarily the best coupling. There's an idea of a best coupling in the Markov chain literature that could be very complicated to sample from. To the best of my knowledge, there's only one case where we know how to sample it in an MCMC case. But because we're not using the optimal coupling, we're only getting an upper bounds that are no guarantees to be sharp.
Can you comment a little bit, please, what that optimal coupling is?
Okay, yeah, sure. So if you look at the TV distance between those two distributions, so this is the distribution after t steps of a chain that starts exactly at little x. And this is the distribution after t steps of a chain started at little y at time 0. If you look at this, in a surprising generality, there is a coupling of those chains such that for that coupling, you would have an equality here between this distance and the probability that the meeting time occurs later. So but it's always the case that you have, so these probabilities, again, under the chain started at x and y. And this is kind of always true for all couplings, the inequality. But it turns out the equality holds for something that's called, let's say, the optimum coupling. There are papers by, for example, Pittman, 1976. But the construction is very, you could wonder how to implement this coupling, of course. But in this example, the construction is like you first sample the meeting time, and then you define the trajectory of the chain from the meeting time and point backwards to x and y in a way that in MCMC settings, like we wouldn't necessarily know how to start. But it's interesting that it exists. And it turns out, since last month, I know that there's a certain coupling from Metropolis Hastings, but with independent proposals that achieves this. But I was discussing with Guanyang Wang with that Broadgers. Okay, so in Wasserstein distance, you get similar plots. Wasserstein distance, you don't really know about a reference point. So in TV, you know that the value is between 0 and 1. In Wasserstein, there's a lack of sort of reference value to know if you're at a small value or not.
What's the number, capital R, that you choose? How is that? Does it just make it smoother?
Yeah, exactly. It makes them smoother. You can see that, for example, here, there's sort of crossing, which shouldn't happen. So that is due to R being not infinity. So yeah, it's in a sense, the meeting time is a one-dimensional, integer-valued random variable. And so it feels like in order to estimate its expectation, you shouldn't necessarily need a ton of draws, right? But what I should probably be doing is simultaneous confidence bands, like Jose. That would be helpful here, to have a sense of uncertainty. Yeah.
So in the Wasserstein distance case, is that easier to compute the bound because you're computing expectation of the distance rather than expected time of the expected power?
No, it's really in terms of complexity, is very similar because TV is like using the 0-1 distance. And so here it's using the Euclidean distance. But so it's very comparable. You don't need to store the trajectories also because you can compute, the cumulative sums of distances along the way. And so. I was saying it's not easy to interpret the value. It's not quite true because there's a relationship between the distance between the first moments of the distribution and the Wasserstein one. And the distance between the first moments of distributions is not something completely abstract, right? You could have a sense in your problem that it's a small distance between two means. So yeah, you could potentially interpret those values as well. But I feel like for TV, whatever the problem, TV is always this thing that you want to be. 0.01 is a good small value for the TV. Because it's also the sum of all the difference between probabilities assigned by the two distributions to any sets. And so, if you want to make a probabilistic statement about pi, and you want to not be 0.01 away, you know that you should use your TV at 0.01. And so I feel like it's easy to convince yourself that 0.01 is a small value in TV than it is in one Wasserstein. Okay, I'm completely going to skip. There's a whole bit about how we can estimate the asymptotic variance in the CLT. And now I'm going to move on to how do we generate those coupled chains? Unless there are questions. Yeah?
Just like a clarification question. You were writing down on the board the definition of meeting time. I'm talking about the construction of those couplings. And
yeah.
we were talking about xt given xt minus 1 is given by that transition probability kernel. Could you remind us whether that same restriction applies to the second, to yt? Does yt have to marginally equal?
Yes. Yeah, thanks. You're right. I should never have erased this. The coupled kernel P bar. Actually, yeah, I think I have slides for that coming up. What do we need to do now? What do we need to do? We need to design this coupled transition P bar to satisfy a certain number of conditions. And so first, indeed, we want both xt and yt to follow the same original Markov chain with transition P. So when we draw xt, yt from P bar, here I remove the lag. It's the same construction for P bar, whether there's a lag or not. So given xt minus 1, yt minus 1, I want that if I just look at xt given xt minus 1, or just yt given yt minus 1, this follows P. So if you look at either of the two chains on its own, it would look like it's the same Markov chain. But we also want a meeting. So we want it to be possible that xt would be exactly equal to yt at some point in the run. And from that point onward, we would like that the chains continue to be together. So in the poetic language of Markov chains, this is called a faithful coupling. So once the chains meet, they stay together forever. Okay, so how do we do that? So I'm going to take a step back first and talk about static distributions instead of Markov chains. So now let P and Q be two distributions. Could be two normals. We're going to look at the case of two different normals. Now a coupling of two distributions is a joint distribution with the given marginals. Okay, so It's a joint distribution for x and y such that if you integrate y, you get first distribution p. If you integrate x, you get the second distribution q. So for two distributions, we looked at TV before. There are different equivalent representations, and in particular, the one based on coupling, infimum over all couplings of the probability of them being different. Okay, so it turns out that this infimum is attained by what's called the maximal coupling, which may not be unique. We're going to look at a few. So there is a joint distribution with marginal p and q, such that if you were to draw from that distribution, get an x and a y, and the proportion of the cases where x would be exactly equal to y would correspond to 1 minus the TV. Or the proportion of cases where x is different from y corresponds exactly to the TV. Right? And the TV is not necessarily 0 or 1, so it means there could be a sizable proportion of pairs that you draw from that coupling, such that x is exactly equal to y. So let's look at two, here I think it's two Gaussians, with different means and different variances, p and q. So the TV distance between those two distributions, you can compute it in different way. For example, it's 1 minus the area under the pointwise minimum, here in a dashed line. So you see, it's a sizable area. I don't know, maybe it's equal to 0.6 or 0.5, whatever. So that means there's a way of sampling xy, where x follows p, y follows q, but 0.6 proportion of the pairs are such that x is equal to y. Which is funny, right? So clearly, if you sample from an independent coupling, in this case, you get 0 proportion of points that are equal. So very intuitively, before showing you the algorithm, if you draw from p, and you get, you get those real values, so it's maybe 1.23556661, and now you have it. It's not written anymore on its forehead that it came from p, right? So maybe it could have come from q, right? So that's the spirit a little bit. So let's try to think about whether we can take a draw from p and accept it as a draw from q instead.
But do you know the explicit form of that maximal coupling? Do you know that if I just give you two distributions, the TV, you can just sample from any TV?
You know more or less things depending on what you know about p and q, but I'll show you an algorithm that samples from it. So in a sense, that's a very, it's coming up. Yeah.
Okay.
Yeah.
Just maybe a question for Jose, if he's around here, but is he around here?
No.
This seems like the type of stuff that could be used in these DRO papers to try to motivate attacks.
Ah, yeah.
So say if you corrupt covariates, I guess you could define attacks by covariation.
Yes. Yeah, it could be because they use TV to relate the contaminated and the non-contaminated distribution, right?
I haven't really seen with the total variations, but it seems like Jose would know this type of
Yeah.
This thing sounds, especially for classification problems, sounds very different, right? It's just very natural.
Mm-hmm. Yes, I mean, it could well be interesting to chat with you. Mm-hmm. But here, of course, I'll be interested in the sampling aspects of this, but there could be many other situations where this comes up. Okay, so first I'll show you the result of the algorithm that I'm going to show you next. So this is a scatter plot of points, of pairs of, I think there's 10,000 of them. So x, y, where x follows p, y follows q from the previous slide. And you see that lots of points are exactly on this line, and this is the line where x is equal to y. Okay, so next I'm going to show you how we implement this algorithm that returns this. Okay, so it's a weird joint distribution. It has a sort of a degenerate part, you could say, because this is supported on a curve, on a line, in fact. And there's a non-degenerate part here. here, where, in fact, if you condition on being on the non-degenerate part, X is independent of Y here. And this is just one of the multiple maximal coupling that you could think of. So the fact that it's maximal is the fact that there's as many points on that line as can possibly be under the constraint that X follows P and Y follows Q. Yeah.
So when we're designing this algorithm, do we have knowledge of when we want these two sequences to meet and stay wherever? Do we have a knowledge of the meeting time?
No, we don't have a priori knowledge of the meeting time. So here I'm showing just static distributions. We'll go back to the Markov chain case later. But essentially, the Markov chain evolves by, iteratively sampling from static distributions. Well, they're not static because they're depending on the current situations, but this would correspond to what we do at one step of the coupled chains. But we don't know how long it's going to take before we hit the line. Yeah, exactly. That would happen, yeah.
That's going to be interesting.
Yeah, what's going to happen is that once we hit the line, we'll stay there. Yeah, indeed. I mean, when I say we don't know when it's going to happen, so if you do a theoretical study of MCMC, that's what you're trying to figure out. When you do those convergence bounds in TV, you're trying to figure out when the chains would meet. But here we're looking at a much more empirical stance where we're going to take a practical MCMC algorithm and we're going to try to make the chains meet without doing any theoretical analysis of anything. Okay, so this is the algorithm. Okay, so I'm going to go through it. First comment, it fits in one slide. Okay, it's not that bad. Okay, in that sense. So there's an input of this algorithm. The input is that we can evaluate the density of P and the density of Q. So for normal distributions, no problem. And we can sample from P and from Q. Again, for normal distributions, no problem. But here also you could replace normal by any of the familiar distributions implemented in Python and R, and you could run exactly that algorithm. Okay, so what do? We sample from P, we get the X. And then there's going to be two cases. Either we're going to set Y equal X, that's when the pair is identical, or we're going to do something else to obtain Y, but still we're going to output X. Okay, so X is only drawn here, so it's clear that X follows P. Okay? It's come from P and we don't do anything to it, so we obtain a pair and for sure X follows P. So now we have to discuss a little bit about Y and to decide whether it follows Q. And if it does, to see whether sometimes it happens that X is equal to Y. So, does the algorithm sometimes stops at the first step? And does that happen with the maximal possible probability? Okay. And if that's the case, then we have sampling from a maximal coupling. Okay, so I was thinking I could do a bit of a justification for this. And then the rest is going to be more like flashing pictures. And then looking at a practical MCMC algorithm where we're going to try to see where those kind of techniques can be used as a subroutine in coupling chains. Yeah?
Just to clarify, you mentioned that there are many maximal couplings.
Yes.
When we run this algorithm, is it the case that it's going to give you samples from a particular maximal coupling?
Yes.
It's taking a sample from each of those possibly many maximal couplings is the one we sample from?
Yes, that's right. In fact, when you have a procedure to sample from a distribution, that uniquely defines the distribution. So this is, I'm not showing you the joint distribution in the form of a joint PDF or something like that. You can see the output of this algorithm here, so you can guess that if you were to try to get a density representation, it'd be a bit complicated. Not that complicated, but you'd have to separate the part that is supported on the line and the part that's supported on R2. And then there's the density associated with both of those parts. So it's absolutely continuous with respect to this mixture of measures. But you know, and you can find representations in the literature. But here I'm going to say that, you know, this completely defines the joint distribution, and it's exactly what you implement. But also, of course, then, well, let me just flash another picture that corresponds to another algorithm. This one. So here it's a bit different because there are two normals that have the same variance. Again, a joint distribution, but here the points are either on the line as before or on a half line. Okay. Well, it's kind of on the T. So there's an algorithm also in the slides that samples, that obtains these points. But this one only works for some distributions.
And just to confirm, if we were to have run the algorithm that you had run before on the case with, actually maybe that is the question I'm asking, was this generated from the algorithm that you just flashed on the previous slide?
No, so this one is generated by the algorithm we're going to look at in details. And here there are different variances, but you could, if the variances were the same, it would look very similar. You would, I just chose the standard deviation to be 2 and 1, but if you do 1, 1, it's like relabeling the y-axis.
And so just to make sure I follow, the amount of mass that's based on this picture on y equals x is the same as the amount of mass that's based on that.
Absolutely. Yeah. So there are different joint distributions. They're both maximal because they put the same and the maximal amount of mass on that line. But they are obviously different. I mean, it's obvious to see that they are different when you look at the scatter plots.
The other one is also maximal?
This one is maximal also. Yeah. And the previous one was maximal as well. This algorithm that we're going to look at in details leads to that picture. But in the slides, if you want the algorithm for this picture, it's this algorithm. So it's also fitting in one slide.
But then the other one, just one question. So the first step of the algorithm, so you're sampling from P.
Yep.
So you're looking at the likelihood ratio Q over P.
Mm-hmm.
So if you were just doing testing, kind of like you testing the known P against the alternative Q, you would typically reject the null when Q over P is large. So
Yeah.
so if I want to set y equal to x, intuitively when that Q over P is large enough, is that what?
Yeah, so because, you know, so you draw from P, you get X. Is it plausible that this is a draw from Q? It's more plausible if Q of X is large, right?
Yeah, absolutely. If the likelihood ratio is large.
Right.
QX, which is what you have on the right side.
Exactly. So you're more likely to accept it if Q is large at X.
But the uniform that you have over there, all right, because it's 0, 0, 1, right?
So also you know that if Q is actually exactly equal to P, then you always accept at the first step, and then of course you return the same, you return XX every single time.
But if Q over P is always larger than 1, which means that Q is more likely to also, what's the part that I think is confusing?
Yes, but you know it's densities, so they're normalized, so Q cannot be always larger than P. Actually.
No, I know, but for the draw, right? Like if you give me a draw for which Q is giving a higher likelihood
Right.
to P,
You're sure to accept it.
I'm sure to accept that. Okay.
So that corresponds to, it's kind of complicated to see there. But you see that there's this bit here where there's none of the y values here that do not correspond to an x equal y output, corresponding to, I think, what you are hinting at.
Yeah, that's very interesting. So for the other part, if I in the other case, what I'm doing is just sampling jointly
Right.
from Q and W star. Oh, here I get that again.
Yeah, so here it's, it may look a lot like a rejection sampling type of algorithm. You have a while loop, you repeatedly sample until you accept. Yeah. And it is, in fact, a rejection sampling algorithm. And that's how we're going to justify it. Right. Yeah. But let me go through the proof. It wouldn't take too long, I think. So So hopefully it's clear that X follows P because we basically draw it from P and then we don't change it. So we need to check that Y follows Q. So for that, we're going to compute the probability that Y is in a certain set. And we're going to hope that it's Q of A. Okay. But that's going to happen either because basically we're stopped in step 1 or we stopped in step 2, right? Because this is a partition of the possibilities. Okay, so let's see what happens. So compute separately the two terms. So if Y is in A and we stop at step 1, that happens with the probability of, so I'm going to write things in terms of integrals. So that happens if, so we're integrating over A, and then we're going to integrate, so there are two sources of randomness in that first step. There's a draw from P and there's a draw from a uniform. So that's giving us a double integral here, where we have that W was less than Q of X divided by P of X. And then there's a dW, because that's the density, it's just one, the uniform density. And then there's a P of X dx. Right, so that integral, I'm going to say that this one is for W in the sense for X. Okay, I can write this. This is the probability that we stop at step 1 and Y is in. Oh yeah, so I could put an indicator that Y is equal to X here. I'm just saying Y is X in that case. So we're just looking at whether X is in A directly, and the uniform was less than Q over P of X. Right, exactly. So actually you have a minimum. So because the W cannot be more than 1, so if I just do the first integral, I get the minimum between 1 and Q of X, P of X. Good. And then I have P of X dx. Okay, and I'm just gonna, you can imagine P going in, the minimum. So in fact, you have the minimum between P of X and Q of X. Okay, now we can already see why it's going to be a maximal coupling. Because the X is going to be equal to Y if we stop at step 1. Step 1 is outputting X equal Y. And so if we want to say that, what's the probability of stopping at step 1, we can take here A to be the entire set. So we have an integral over the entire set of the pointwise minimum between P and Q. That was one of the representation of 1 minus the TV, I think. Right? So from here, we know that probability of step 1, which is the probability that X is equal to Y in the output, is exactly 1 minus the TV between P and Q. Good? Okay. So it remains to check, though, that the second step does something, because here we haven't used the second step. So what should he do? He should make sure that marginally Y follows Q. Okay. So here we have computed this probability, but we would like the sum of step 1 and step 2 probabilities to be equal to Q of A. Can I erase the bottom part? Yeah. So, because we computed the first part, we know what the sum should be. So now we want to check that the probability that Y is in A step 2 is equal to what it should be in total minus what we obtained for step 1, which was the pointwise minimum between P and Q, integrated over the set A. So we need to check that this works. And then we will have that indeed, because this is for any A, so that must be that Y follows Q. Okay. Okay, so it's not obvious, right? It's not obvious. I mean, we can put this in the integral if we want. We have integral of q of x minus the pointwise minimum but that doesn't appear directly visibly in the second step. So we have to do a little bit of work. But we may recognize the form of a rejection sampler where we draw from Q, that's our proposal. And it's not clear what the target is, but we know what the acceptance is. And so from that, we can sort of reverse engineer what the target should be. And also from here, we would like, in fact, the target to be basically this. But this is not a density. This is a density minus something positive, so it needs to be normalized. So here I'm going to do something. I'm going to do a definition of R of x, the sort of remainder probability from Q. It's going to be Q of x minus the pointwise minimum, but normalized so that it's a proper density. So it's divided by the integral of the numerator, which in fact, again, is the TV, because it's the integral of Q, which is 1, minus the integral of the pointwise minimum. So here it's let's call it just TV, but it's the normalizing constant of this distribution. Okay, so maybe we can try that the idea that this is the target in the rejection sampler. The proposal is Q. Okay. So now, new game, you have a proposal Q, you have a target of this form, you implement a rejection sampler. What do you need to do? You need to find an upper bound on the ratio target divided by proposal, which is not always easy, but in this case it's easy. Because if this is the target, proposal is Q, right? But the top is always less than Q. So an upper bound is 1 over the TV. Okay? That's a constant value which we know upper bounds the target to proposal ratio. Okay. Okay, so then actually, from that point onwards, it's exactly rejection sampling. So we just need to check that it is exactly rejection sampling. So if we were to use this in a rejection sampler, what would the algorithm look like? So we would sample, so I think it's called Y star from Q. And we would sample, say, V from a uniform until it should be the ratio. It should be that V is less than the ratio of the target over the proposal, but with this upper bound. So it was pi over m times Q before. But if you compute that, now it's Q of x minus the pointwise minimum just divided by Q. Right? Because the bound is the normalizing constant, basically. So if I do target divided by the bound, I just get, again, this unnormalized density. So I get this, and what is this? This is equal to 1 minus the minimum between P over X over Q over X and 1. Okay? So now we need to check that sampling V uniformly and comparing it to this is strictly identical to sampling another uniform and comparing it to that. And it turns out to be exactly the same. Okay? And why do we have a minimum here that doesn't show up here? Because here we could also put a minimum if we want, right? In the sense that if this was larger than 1, it would never be the case that the uniform would be greater than it. Right? So I'm just trying to work on the expressions on both sides to make them match. I think if you do that trick, if you want to do the details, you also find that you would be comparing 1 minus V. I mean, we can do it so that we've done the whole thing, maybe. So I'm going to put V minus 1. It should be less than this minimum. So it's the same as saying that 1 minus V should be more than this minimum. But 1 minus V is also a uniform. So that I can call W star. And being greater than this minimum is the same as being greater than just the ratio, because yeah, in the event that this ratio is more than 1, for sure W star is not greater than it. Okay? And so the second step does the rejection sampler that has the target that makes the sum of those two probabilities, step 1, step 2, exactly equal to the Q of A quantity, which means that Y follows Q. Okay?
So there's nothing about normals here, actually, it's for...
Oh, yeah, it's completely generic.
So it's like when the linear pairs want to do this to get the gravitational bound, they see like draw the two plots on the area of the union.
Yes.
If it's in where they overlap, keep it. Otherwise, draw in the tail. And then it seems like if you're using Q as the proposal, then it seems like the drawing the tail from Q and keep only if you are a non-overlapping part. You can, with what you've written there, you
Yeah.
can see that as rejection sampling.
So it's a different algorithm than what they describe.
Okay.
What they describe would correspond to something that you cannot do in as much generality, I think. And that's why, but you can do it in discrete cases, and it's a good idea to do it, because you avoid the while loop. But so basically, what we've just seen, the algorithm, works as follows. You draw from P, and then you try to accept it as a draw from Q. And you remember, if Q is greater than P, you always accept, right? But otherwise, you may not accept. And if you don't accept, then you're drawing from Q, targeting, so you're doing rejection sampling from Q, but targeting Q minus P. So what is Q minus P? Minus the pointwise minimum, sorry, minus the pointwise minimum. So Q minus the pointwise minimum is basically the bits here above the dashed line. Okay. So that's the procedure. You sample from P, you try to accept, otherwise you're rejection sampling from Q to hit only certain parts. But what you could also be doing is you can split, this total mass into different bits, and you can sort of have a mixture distribution approach. You can say with some probability, I'm going to sample within the pointwise minimum, and that I can assign to both X and Y. But with the remaining probability, I sample from either this top gray bit for P or this side bits for Q. But in order to do that, you need to know how to compute the mass under the pointwise minimum. So you need to be able to perform this integral. And that is okay in dimension 1, probably, but it turns out that you don't need to do it here. But it will draw from the same joint distribution, actually. So those would be...
Because I need to know how much of the mass is left in both non-overlapping parts.
Yeah. So in the theory, it's perfect because you... But just the quantity, the weight assigned to that common, that overlap is not something that you know if I just give you P and Q. And this works also in multiple dimensions, this algorithm. Yeah. Okay. So now you're convinced, okay, we have two different normals. They could have different means and variances, but it could be that we can draw a pair following them, such that sometimes X is equal to Y.
You get the same intuition coming in that's going to be maximal because you really exhausted the whole overlapping part.
Yeah. Okay, so there are others. This one is called a reflection maximal coupling, in the sense that, so a reflection coupling would be simply for normals that, if you do a positive increment for one, so positive deviation for the mean, for one of the two distributions, you do a negative increment for the others and vice versa. It's called a reflection coupling, and it's used in there's a big paper in the 80s on reflection coupling for Brownian motions. So if you have Brownian motions, you can evolve them independently. In 1D, they would eventually cross. People have been wondering, the time it takes for them to cross. And you could wonder how to couple them in such a way that they cross the fastest, at the earliest time. And so it turns out, for example, if you use common random numbers for Brownian motion, they would never cross, right? They would move parallelly if you do common random numbers. If you give the same Brownian motion to starting from different points, they will never meet. But it turns out that if you do the reflection, so it's going to be tricky to draw correctly, but I'm going to try to reflect this. So giving basically minus the increment of the other to the first. Something like this. So they cross then, and it turns out it's the fastest way to make them cross. Okay. So it's called a reflection coupling. And so here you have a sort of hybrid beast that's trying to put as much mass on the diagonal, but in the other case, it's trying to do the reflection. Yeah.
So if I'm keeping track of the narrative, the reason why we're interested in maximal couplings is that we were thinking about coupling two things together
Right.
so that they can meet. And one way to quantify that meeting time is to design couplings so that once they meet, they stay together.
Right.
You described here on the board, if you were to use common random numbers, you would have these parallel chains. And so if you were to reflect, you would get them to meet. That approach to come up with the maximal coupling, maybe I'm just repeating, maybe I'm losing sight of the bigger picture.
Okay.
Like that solves that bigger
Sure.
picture.
Yeah. So in a sense, we could make them meet here without doing maximal coupling, just by reflection. But this is because it's a continuous trajectory in continuous time, right? Even if you do a discrete time random walk, in that way they will never meet, right? But it's still just to give some sense that, couplings have been looked at for a while. People have been trying to make chains meet for a while. And that literature, which is rich, in fact provides good ideas for MCMC practical couplings. And so this one in particular, we've been using it with some success in the case of random walk Metropolis Hastings, for which it was not invented. But I just wanted to also show that there's not only one maximal coupling. But let's go back to, indeed, the core topic, which was more MCMC. I had more funny pictures of couplings. This is an optimal transport coupling, which is well known also to be degenerate. So it puts all of its mass on a curve here. So the optimal transport coupling means it's the coupling such that the distance between x and y in expectation is minimal. And it's obtained in 1D. It's actually obtained with common random numbers, in a sense. So if you do x inverse CDF transform of a uniform, and you give the same uniform for a y, oops, that's an equality, obtained with inverse CDF transform to use the same u. So this is the quantile function. I'm saying a pseudo-inverse of the cumulative distribution function for x and y, or for p and q. So in 1D, if you give the same uniforms, you can see that y would be degenerate, right? Because you have two deterministic functions of the same variable. So they are very much related to, you could guess the x from the y and vice versa. So that's why they lie on a curve. And this would be the way of making them as close as possible in expectation. But here they may not be exactly the same. They may not meet. So the line, it would cross actually the line of x is equal to y. It would cross, but only in a singleton or a couple of singletons. Okay. So just to say that there are those ideas, those ingredients. I see that as ingredients, and we're going to mix and match to make MCMC chains meet.
So quick clarification.
Yeah.
Those P evaluations should happen at one start.
Those P and Q, yes. Yeah, I've used X here because I lost track of my notation. It should be Y star everywhere. Yeah, sorry. Yeah, thanks. Okay, so now I have two examples. The probit that we've seen before. Yes? It's funny, huh?
So say, for the first coupling that you described, or for any
No, so it's what you're asking in a sense is comparing TV and Wasserstein distances.
Kind of what I'm trying to do, yes.
Yeah. And so, there's no, I mean, on compact spaces you can do some ordering, but there's no general, the way I understand it is, in Wasserstein you want to be in average, not too far, as close as possible. You don't have to be sometimes exactly at 0 in order to have the best expected distance. Whereas the maximal coupling, it's trying to put all in, if you want, all the degrees of freedom in the choice of coupling on the possibility that x is equal to y. And then what do you do otherwise? Well, that's where there are multiple maximal coupling. So you could minimize the distance. I used to have plots for that. You could minimize the distance between the remainder probabilities that you have after having removed the overlap. You could do that. Although numerically, apart in 1D, I'm not sure how to do it, but yeah. So you could, in a sense, have an optimal transport / maximal coupling, where in the same way that this is reflection maximal, you could have OT maximal. If you wanted to sort of put as much possibility of x equal y, but also sort of have the best possible expected distance in the other case. But TV on its own, yeah, it's Wasserstein with 0,1 cost. Yeah. Okay, so let's try to couple MCMC stuff now. Oh yeah, I want to say also, I did not come up with this. Really, it's something that I had no idea about, and all of my colleagues in MCMC seem to have had no idea about, but actually, there are books on couplings, like probability books, like Thorison, called Coupling, Regeneration, and Processes, or something like that. Which first version is in 95, and it mentions this algorithm as a side note, like after explaining total variation distances and the coupling representation, there's a side note about how you can do that. So it's kind of like it was out there. I can't know for sure what's the first instance, but it seems like the people who came up with it didn't. I mean, I think, if you were to really think it's possible, if you believed, if you are a believer, and you try to do it, given the inputs of being able to evaluate P and Q and sampling, you would come up with it. It's not that complicated if you know about rejection sampling. And so the people who first explained it didn't make a big deal out of it. There are papers by Pierre that sort of have variants of this. Yeah. Okay, so maybe 2 MCMC examples. And that's going to be it for this. There's a bit more in the slides. This one we've talked about before already, so let's try to see how we couple it. So, probit model, binary response, or outcome variables, and covariates X. We want to do it in a Bayesian way with a Gaussian prior. And that leads to a posterior distribution. But also, we can have this augmented variable representation with some Zs. Then we have a joint distribution of beta and z given the data. And we can alternately update the beta given the z and update the z given the beta in what's called a Gibbs sampler. Here I'm going to use some data from this study, impact of subsidized health insurance on the poor in Colombia. Well, there's about 13,000 rows, which means 13,000 z's here, because there's one latent variable z for each row. But it's only 10 betas, 10 regression coefficients. Okay. So this is a reminder of what the algorithm is doing, the MCMC algorithm, just for one chain. It's updating each of the z, given the rest, in a univariate truncated Gaussian way. So it's depending on whether the corresponding y is 1 or 0, we sample from a truncated Gaussian. I don't know how much you remember from that. We went quickly over this, but so truncated Gaussian. So it's a Gaussian, but the mass is truncated. So either it looks like if you have a Gaussian, but either it looks like it's truncated on the left, so it's like this bit, or it looks like it's truncated on the right, so it's like the bit on the right. Actually, a whole literature about how to sample particular multivariate truncated normals. But in the univariate case, it are like R and Python packages. You just type R trunc norm, and that's it. Okay. Okay, and then once you have updated the z's, you have the betas. And the beta, they're nice and conjugate with the prior that was chosen for that. So you refresh them by sampling from a multivariate Gaussian. Okay, so now what's the game? The game for us is to imagine two chains. So each chain has a set of beta, a set of z's. So you have two sets of betas, two sets of z's. And you want to make the two chains evolve while respecting this evolution, but jointly so that maybe at some point all of the beta for one chain and all of the beta for the other chain would be the same, and all of the z also would be the same. So note, if you manage, for example, to make all the z equal, then what happens here, you would have to sample the two new betas from a Gaussian that would have the same mean and the same variance. So you're done now. Okay? So if all the z's are equal across two chains, the next update of beta will make them exactly meet because you're supposed to sample them from the same distribution. So you sample one and you say the second one is equal to the first. Yeah? And likewise, if you happen to have the same betas, you manage to couple the betas so that they're identical at some step, then all of those truncated Gaussians are the same across the two chains. Right? So now you don't have to do anything special to make the z's equal to across the chains. Okay, so we can try different things, right? We know how to couple variables a bit. We can do some maximal couplings, either of the betas or of the z's, one by one. We can do some optimal transport couplings. We can do different things. And the goal is to obtain couple chains that meet as quickly as possible. So if you just run one chain, this is the trace of the betas, so you couldn't tell for sure whether it would take 100 steps or more to converge. Now we're going to have two states. So I'm going to call beta z the first chain and beta tilde z tilde the second chain. How do we make them meet? So do you have any suggestions? How are we going to proceed? If we do nothing, if we sample them independently, they will not meet. That's for sure. Yeah. We could use common random numbers, but they will not meet also, right? Maybe they'll get closer to one another or something nice would happen, but if everything is common random number, they will not exactly meet. We can do maximal coupling everywhere with the algorithm. But maybe that's not the fastest way of obtaining meetings. But we could do that and see what happens. Yeah, I mean, there's a chance that they would meet, right? So would that happen in a reasonable amount of time? Usually myself, when I implement those things, I have no idea how long it's going to take, right? So I try on a small problem and I make it bigger, and eventually when all the data sets works, then I'm happy. Yeah.
Maximal coupling after they meet isn't guaranteed that they stay together.
Yeah, that's a good point. Yeah, actually, what you can do once they meet is just sample one and say the other one is going to be equal to the first. So you don't have to worry. But actually, if you were to use that, so in the code, usually I have a flag, have they met? If yes, then I stop trying to do some coupling. But in fact, if you were to have P equal to Q, so if they were already at the same place, the conditional distributions would be exactly the same. And so then actually, this algorithm will always terminate in the first step. You still don't want to do it for numerical reasons, right? You don't want to see whether if you do a ratio of densities or you would actually get exactly one. You don't want to try it. So you would implement this on log scale, but yeah.
That last point, I followed. How does that algorithm respect what has happened in the past? How does it know that you've met so that they can stay the same?
Well, I mean, in the implementation, once they meet, I know they could remain the same by just sampling one and saying the other one is equal to the first. So I literally implement that. I don't try to make sure that my coupling implementation is resilient to numerical imprecision. So I just say, I just flag meeting, and from that point onwards, I don't use couplings.
Maybe I misunderstood that. What I thought you were saying
It would. Yeah. It should.
I don't think I follow.
No, it should, because if you sample from x from p and you compute q over p, but q now is equal to p. Q is equal to p because the conditional distributions are the same now.
I see.
Yeah. So if all the z's are the same across the two chains, the distribution of beta given z is now the same. But still, it could be that your numerical implementation, well, I think it would work in many cases, but I just don't want to. It's also just faster to not do that. Okay. Okay, so what did I try? So I tried common uniforms and inverse CDF transform for the truncated Gaussians. So I don't try to make the truncated Gaussians become equal. I try to make them sort of be not too far from one another. And then I did this reflection maximal coupling that I showed you for the multivariate Gaussian. And it seems to work quite well, so I was happy. Right? I have no result about this is the best thing to do. You should do that. So I try something. And what happens? So I have meeting times. It's a funny case here where the meeting times have a bimodal distribution. Okay. So here I'm showing what happens when I generate maybe 100 or 500 meeting times. So by running chains until they meet and recording the time for each run. And I show meeting time minus lag because if you remember, I want to know how long it took for the chains to meet from the time I started to try. So whereas my tau variable is defined as the first t such that xt is equal to yt minus L. So I remove L to say this is the number of coupled transitions that I executed in order to get a meeting. The full 13,000 things have become the same. And you can see why it's not crazy. Sorry? Yeah, because if the beta gets to meet, and not only in dimension 10, then automatically all the conditional distributions of z become exactly the same. And then you can just, So it looks like a daunting problem in the first place, but there is and that's usually the case in MCMC when things work well. I mean, if it was a fully dense, intractable 13,000 dimensional problem, the original MCMC algorithm would have taken way more steps to converge. Yes. Yes. Yes, but I could easily have tried, and in fact in my original work on this, not the Glynn and rework, but in the work with Eva Chade and John O'Leary, we basically did maximal couplings everywhere. We were a bit less savvy by then. And so that still worked in some cases. Yeah. But
the idea would be like all these tools and then you give some kind of tricks up the trade.
Yeah, no, that's a big open, and I wanted also, of course, to share open problems, because this is a graduate school, so there's a lot of open problems. It's something, I think it works quite well enough to be interested in this, and so I'm happy to describe those problems, but there's a lot of things we don't know. And every time I try a new problem, I'm quite happily surprised that I don't have to wait longer for my meeting times. I'll show you a new problem I tried this week with the quantile regression. It seems to work, but there's nothing guaranteeing it, and there's many strategies. It would be nice to have much more guidelines about what to try, in what order to try. You can imagine it gets quite combinatorial because, if you have many types of updates and each of them can be done in different ways, the combination of things to try is crazy. You could even imagine some sort of reinforcement learning approach to it where you're not trying by hand. At the moment, I'm just trying by hand, but. Yeah. So here I get those meeting times. And just, more concretely, well, maybe hopefully intuitively, you see that if it takes a few hundred steps for chains to meet, that tells us that this is also the right order of magnitude of steps for convergence, but I have these TV bounds to make that link a bit more formal. So those TV bounds in the form of expectation of this function of tau that I showed you in the beginning of this lecture. In this case, it gives this series of upper bound. And this is a Monte Carlo estimate, right? So it'd be nice to have simultaneous confidence bands and so on. But it sort of indicates that maybe less than 500 steps is enough for this problem. And maybe it does converge in 100 steps. Maybe it's, the real rates could be, well, it could be higher because this is only an estimate, so this could be a wrong estimate. But if we trust the estimates, because maybe we've done a lot of runs, and we have a confidence band, then the real rate could be much lower, but at least I get something that is not crazy. It's practical in the sense that, in fact, most people would, by default, would do many more steps than that.
The first graphs that you showed us, so what were you doing exactly to generate those graphs? That was just like the yellow, or you showed the graphs of the betas in different colors?
Yeah, this is just if you do one chain, just one chain, but it has 10 different betas.
Yep.
So I'm looking in one plot at the trace of the component betas over the first 100 steps. Just to say from this that no one would believe that the chain has reached stationarity in 10 steps, but it could be that it's of the order of 100. And with my TV bounds, this is just cartoonish, but I want to say it's just a bound. Yes, you're right. So yeah, they are the Zs, but if I just look at the beta, I have a chain. I have a trajectory. But you can also look at the Zs. This is 10 of the Zs, but there are 13,000 of them. You could look at 13,000 of them. Right? You could spit out a deck of slides and spend an afternoon looking at 10 by 10. Or
So when you were looking at this paper, the probability regression, was it already a paper here that was suggesting to do the Bayesian stuff, the probability regression? Was there already?
yeah,
you just prepared for the context stuff?
And also these simulations I did during the evenings of last year's conference. And the next example is during the last few evenings. But Bayesian probability regression, that's a big thing. Like the Albert and Chip paper is cited a ton of times. Yeah. I don't know, that's another debate whether it's a good idea or not. But suppose that you have some scientifically relevant information about the beta, you want to bake that into the prior information, and then this is not the only way to incorporate prior knowledge. I don't mind the Bayesian inference. I was really trained in the Bayesian world, but then I discovered that a lot of the benefits of Bayesian inference can also be achieved in other ways. So I'm just saying, this is something that people actually do, and they could maybe save some energy, some literal energy by not running chains for 100,000 steps, just by lack of any idea.
So but then the theoretical results that you would bring to the table for a paper like this is so you would give really a recommendation. So for that and the big sampling algorithm.
Right.
Run that particular big sampling algorithm for 400 periods and guarantee that close to.
Yeah, if I just show this, that would be a very applied paper with no theory. So what you could do if you really care about a particular MCMC algorithm, you can try to show how the meeting times behaves with N, with P. We did that with Anirban Bhattacharya and James Jandro in the case of Bayesian linear regression, but with shrinkage priors. So we had 10,000 covariates, but only a few hundred rows, like a genome-wise association studies type of stuff. And we didn't fully succeed, but we are trying to give theoretical results that justify theoretically that the meeting times would scale well with the input of the problem.
Could you get some sort of formula that connects directly the number of iterations for this big sample with the dimension of the vector of covariance?
Yeah, that's what you hope to be able to do sometimes, and people have done in specific cases at this point. But it's a very case-by-case enterprise, right? You're trying to design a good coupling that works well in practice, but that you can still analyze. That's not like a crazy mix of, machine learning devices that you may want to do to optimize the performance. But yeah. So there are papers taking a particular interest in a model, an MCMC algorithm, a coupling or some coupling IDs, and then trying to show how the meeting time behaves. There's a good one in Another Stats 2 years ago about state space models. So it's an MCMC algorithm that was, it's called conditional particle filter with backward sampling, which is quite complicated, which is kind of state-of-the-art to sample the latent process in a nonlinear, non-Gaussian state space model. And they show that the meeting times behaves well with the length of the time series. By which I means linearly, I think, in that case. And that's an analysis stats paper just on this topic. But you can generate lots of, it's incremental from the onset, but if you care about a specific problem, you can try to couple the algorithm, and you can try to show things about it, and that's a paper generation machine, potentially. Which is good to have, right? We always like a good paper generation machine. Okay, just a last example, maybe, to connect a little bit with Guillaume and Blaise talk. So this is quantile regression, but in a Bayesian flavor. So, well, that's just quantile regression at the top with this rho tau function. So for a specific quantile here, I'm going to fix the quantile. And it turns out, so I give the reference in the next slide, I hope. I'm using a Gibbs sampler that was proposed in 2011. Yeah, in Kozumi and Kobayashi, and it's implemented in the package base QR in R by Benoit and Van Den Pol. So I take exactly the same Gibbs sampler. And the idea of that Gibbs sampler, it's a bit similar to the idea behind the probit regression stuff. So you represent basically this quantile, you're looking at this and you think like maybe this looks like minus the log likelihoods of a certain distribution. And that distribution, in fact, would be the asymmetric Laplace distribution. So you define it by taking the exponential of minus the check function. So the model would be yi equal x beta plus epsilon I, and epsilon I follows this. And so you can look at the posterior distribution. So here it's funny because there's this scale parameter sigma, which was nowhere in the original problem. And they put a prior distribution on that. I don't know if they could have just set this quantity to 1, or if there's a good reason to put a prior, but they put a very flat prior on this. They put a normal prior on beta. So at this point, you could say, well, I can evaluate this likelihood easily. So I can do random walk, Metropolis, Rosenbluth, Taylor, Hastings. But they don't do that because I guess if that was what you were doing, you would have to choose the proposal. Sorry, bless you. You would have to choose the proposal distribution. And so instead, they devise a Gibbs sampler, which is tuning free. A bit like the probit regression model. The Gibbs sampler was saying, you sample from those truncated Gaussian, you sample from those conditional Gaussians. There's no tuning. People like when there's no tuning, by the way, but in a sense, it's always bad news because it means if it doesn't work, there's nothing you can do, right? Whereas, so in my experience, it's kind of it's a good first, it gives a method that's a good first trial, but actually, it's, if it doesn't work, then you're back to square one. Whereas a good choice of proposal in Metropolis type of algorithms can go a long way. Anyway, so they propose this Gibbs sampler using a clever representation of this asymmetric Laplace distribution. So if they write this model in this way, then epsilon I follows this Laplace, asymmetric Laplace, and it's the same as this kind of sum of two terms where nu I is sigma times zi, where zi is exponential 1, and ui here, so here there's a square root of an exponential, and then ui is a Gaussian. Okay, so that's a fact of probability that this epsilon I written this way is following that distribution. But once you have this, basically you can augment your variables. Instead of having just beta and sigma, you can augment with the z. There's many ways of doing it, and this is not the only paper on the problem. But this is the one that's implemented in base QR. And so that leads to this. Okay, so I'm making it a bit short, but you end up with 3 updates that you're alternating to generate the whole chain. So this describes your MCMC algorithm. You update beta given the rest. And so here I skip the details, but basically you have a mean that depends on sigma and this latent nu, and a variance that depends on sigma and the latent nu. And I skip the expressions. They're easily computable, but are quite long expressions. So just to clarify also here, again, the nu, which is this exponential scaled exponential. So it's an exponential. This nu, there's 1 for each data point. right? So you have beta, which is the regression coefficient, but you have one latent variable nu I for each data point. And I'm going to use an example from Stock and Watson when there's about 3,000 observations, but only two covariates. So earnings on education and gender. It's among 29th and 30-year-old Americans from whichever decade ago. Right. Okay, I don't know if this is a classic, I suspect it's a classic data set. Okay, so the algorithm is as follows. So you sample beta, this is simply here in dimension 2, but it would be the number of covariates you have. Sigma is always in dimension 1, it's a scale. And it follows an inverse gamma conditionally on the rest. Or you have one parameter that's always the same throughout the algorithm, but the other one depends on the current values of beta and nu. And nu is this vector of size, number of rows in your data. And every time you update it, you draw from the so-called generalized inverse Gaussian distribution. Right, so inverse gamma, generalized inverse Gaussian, is a bit less standard, maybe you've seen them before, maybe not. They have an R package. There is a function to generate from it to evaluate the density and so on. So it's all in one dimension. But just here you have lots of updates, each of one dimension. So that's so in total it's large dimensional, but you can tell again that it's going to be easy because if the betas and the sigma, for example, would be equal, then automatically all the conditional distributions of the news would be equal across the two chains. So the real dimensionality is not 3,000. And that's why it works. So if you think it's cheating, I would say that's why it works. If you have a truly dense 3,000 dimensional sampling problem, it's very, very difficult. Yeah. Like all the large dimensional success in MCMC is because there is some structure underlying this, which the algorithm is trying to exploit. But there's no miracle. Okay, so this is the trace plot of there are 3 betas because there's an intercept and 2 variables. Okay, so this looks like it's converging very fast, in fact. Okay, maybe 1,000 is way more than necessary. So how are we going to couple this algorithm to make sure? Same game as before. Proceed to the cooking part of the process where we're like, okay, we have a few things that we know about. Maybe we're going to have to devise a new coupling, but maybe we can try to first utilize what we have in the toolbox. Yeah. What would you try, Guillaume?
Your trick from before, you make numbers for the last one, and then one of the two clever one,
yeah.
clever one to the top two.
So there's a slight complication here on the beta because the normals, if the sigma and the nu are different, the normals have different means and different variances. So my reflection coupling, it doesn't work. Or it could be extended to that setting, but I don't know exactly how to do it. So I can't use the reflection maximal coupling, but I can just use a maximal coupling. Or I can try to maximally couple these and use common random numbers on the betas. And so I show you what I tried first without thinking for 1 second about it. Common random number on beta. That's easy because you sample from multivariate Gaussian. Here it's in dimension 3, so you can do it via Koleski factor, multiplying by standard Gaussian. So you can use the same standard Gaussian for 2 different Koleski factors, and you sample from 2 different normals. But I could have used maximal coupling and probably would have worked as well. And I use maximal coupling here on every single one of the news. So imagine in the beginning, all the news are different, all the sigmas are different, the betas are different. And you try maximal coupling for all of the news, so maybe it's going to succeed for some of them, maybe not, after one sweep. And now some of the news are the same and some are not.
I think I'm confusing myself when you say you're going to use common random numbers to be able to couple this Markov transition.
Mm-hmm.
So if I'm understanding it correctly, and I don't think I am, but we have these 2 chains.
Yeah.
Whatever way we perturb the betas in this chain is the same way in which we're going to perturb the betas in the second chain.
Right.
I thought we were drawing a picture that says if we try and do that, we're just going to have parallel loop bits, but we're not going to have.
Yeah, that's true, yeah.
And so you're saying that because we have maximal coupling on the other guys, that didn't have meaning on the betas?
Yeah, exactly. I mean, so this is not exactly a Brownian motion or a random walk, right? It's different because I'm not adding anything to the betas. I'm refreshing the betas from a Gaussian. And so this coupling corresponds to the optimal transport. So I'm not saying it's a good idea. I'm just saying I tried this.
Okay.
It's possible to try this.
So for the chain that's constructed, for the coupling that's constructed using this, the hope to get at a meeting time is that we really want the sigma and the news to meet.
Yes, absolutely. Yeah, absolutely. So for the chains to meet now, the sigma must meet. That should be okay because there's only one of them, but all the news have to meet now. And yet it works somehow. So if you look at the TV upper bounds in this case, I tried for two different lags. So when you have a bigger lag of 50, you get a lower upper bound. Again, you don't learn anything before your upper bound is less than 1. So here, you don't learn anything. But overall, it seems like at about 100 steps, one of your upper bound tells you that the true TV is less than 0.01, and the other one says that it's more around at most 0.001. Okay. And maybe it's much less, actually. When you look at the trace plot, maybe it's much less than that. But I claim that this is practical. Like, this doesn't tell you if you do 1 million steps, that's probably going to be good enough. It really tells you like some small numbers. So this is smaller than the default number of iterations in base QR, for example, which is 1,000. But we don't know why. Okay. So before trying, I had no idea why. So what I do is I don't actually do a while loop when I try. I don't let the chains run. I have a hard stop at the 10 steps to understand how long it's going to take, even computationally, to do one step. And then I elongate a bit before I dare to run it until they meet, because you could run forever.
The goal is that like someone who's picked up enough to write a package is able to do the cooking you did and try different things and eventually build these things into the package and use it for...
Yeah, I mean, if it turns out that this coupling or some variants of this works for all the problems where people use base QR typically, then it's useful, maybe.
It could be completely standard.
Everybody should do it, yeah, exactly. So that's the message. Everybody should do it. So just concluding remarks. So Monte Carlo generally is about approximating integrals, computing probabilities numerically. It's useful for many tasks. I mean, I use a lot of Bayesian inference examples. There's a lot of Bayesian examples in the MCMC literature. But there could be all sorts of other cases where you have an integral to compute. Maybe you have latent variables. So you have different reasons to want to, or if you're sampling, test statistic. There are papers on exact goodness of fit test where you have some fancy sampling of test statistic. I'm going to mention it in the talk that I'm going to give tomorrow in the conference.
There's never trade-off between the time it takes to do this and the time you save by doing this.
Sorry, can you?
So I'm going to figure out I need to do fewer steps than I thought I would have from being very conservative.
Yes.
So I need to run your thing to figure it out.
Yeah.
But are they typically on different interval tools or?
It's complicated. I mean, if you look at this particular case, base QR works really well instantly. And I took hours to implement it took me maybe 2 hours to do the implementation.
But just to run it, if someone...
To run it was very fast. I mean, I didn't say it here, but it takes about 2 seconds to do 1,000 steps for base QR, which is implemented in Fortran and everything. So I did not implement my coupling in Fortran. I'm counting on Copilot to do that for me soon. So I just did it in R. And in order to obtain those plots, because I wanted like smooth lines, I asked for 1,000 meeting times. And it took 20 minutes, maybe. So I could have done, a lot of steps. Yeah, so what I suspect could be really helpful is not when you're trying it on your final data set. It's when you're devising your algorithm on very small data sets just to see if it works or which algorithm works better and so on. And then, typically when people try to understand which algorithm works better, they do very long runs and they compute asymptotic variances and stuff like that. But actually, in particular, if you have parallel processing, If you have 1,000 machines, this is really 1,000 times faster, yeah, because you're running stuff completely in parallel. There are caveats to that, essentially. And so if you have access to parallel machines in particular, but you know, this, I mean, on my laptop, which is from 2018, there's 10 cores, and so it's, whereas if you have 10 cores and you run base QR, you can just run it in parallel 10 times, but it doesn't tell you anything more about short-term convergence. So, but yeah, there is a cost, of course, associated to this. I tried to make some connections between Monte Carlo and optimization. There are more. I mean, for example, the coupling techniques that are used in proving convergence. There's a sort of analog in optimization where some algorithms to prove the convergence rate of iterative optimization techniques, sometimes literally the technique is to imagine what the sequence would be starting from 2 points and looking at the distance between the iterates, which is basically a type of coupling argument, like a deterministic version of the coupling argument. And you know, in the last 2 lectures in particular, I tried to emphasize that coupling is a nice theoretical trick, and it keeps on, you know, giving as a theoretical device. So it's useful to analyze modern day MCMC algorithms. But also it's a component that you can really implement, like the maximal couplings we've seen today. And you can think of it as an algorithm that you can really put inside your algorithmic developments. And so, you know, coupling from the past was already doing that in the 90s, and those kind of unbiased estimators more recently. And that's it. Thank you very much.